So as I said, in terms of my element of the presentation, what I want to do is talk about Industry 4 in general terms and its impact with respect to the digitalization of manufacturing. I'll try to give some examples of that impact, but as I said, I want to then move on to talk about the broader impact of manufacturing, particularly on employment in the sector, and how countries like Ireland compete with respect to jobs for manufacturing. So this is a picture, as you can see, Angela Merkel on a shop floor in Germany. It was around 2008 when, in fact, the German government coined the term Industry 4. And as you can see in terms of what she's outlined here, it's that interaction between digitalization and manufacturing. It's very political because it's seen as a transformational impact to the sector, and the competition for jobs in the sector is extremely high. So briefly in terms of background then, we talk about Industry 4 as the fourth industrial revolution. The first revolution dating from the late 1700s was, as you know, steam. The second one was the use of conveyor belts in particular, and the first one was the conveyor belts in Cincinnati. Henry Ford's automobile plant would be another example of that second revolution. The third one dates from the late 1960s and the use of IT and electronics and efficiencies from that. And we refer to the fourth revolution as the cyber physical system. This idea of the cyber world, the digital world combined with the physical world. And what I hope to do in this presentation is give some examples of that impact, and you can see on the right hand side the degree of complexity associated with that fourth revolution. So when we refer to it, it's actually the convergence of a number of different technologies. So at the top of the circle here, we have IoT, or Internet of Things. The use of sensors, and sensors have become extremely cheap and wide-ranging in terms of availability, and the prices as well as size have come down. You obtain a lot of sensor data, you need some way of analyzing that data, otherwise you just become overwhelmed with data. So we talk about big data and the ability to analyze that and integrate that into a process. We look at automation, and I'll talk later on about how automation is taking a lot of manual jobs out of manufacturing. You have to look at the security aspects in terms of, because if the information is available in the cloud, how to keep that secure. We also talk about simulation, and simulation can be a range of things. It can be materials simulation, process simulation, the simulation based on the data. And finally, an area where we're very actively involved is that additive manufacturing of 3D printing, the ability to fabricate on-demand components and fabricate complex shapes with ease. All these technologies converge under what's called Industry 4. So Industry 4 may not use all of them, it can use some of them, but it's that convergence and the impact that they've had is so important. So I'm not going to go through all these technologies, I'll just take a few, and particularly the IoT element, that Internet of Things. And when you look at the table here, you can see the growth in terms of smart devices, like our mobile phones, going from 4 billion to 21 billion in a period of 10 years. The rapid growth of these devices, as I said, it's because sensors, it's because the ability to connect through the web have become so ubiquitous. But in terms of looking at it with manufacturing, I'm going to start with this elevator system. This is from a company called Thyssen Krupp, a German company. And the image that you see there is actually of the One World Trade Center in New York. And it has 102 floors. Its lifts take 60 seconds to go from ground floor to the top floor, obviously if you don't stop. And it has about 320 kilometers of cables just in those lifts alone. In a typical manufacturing operation, we'd look at the lift and we'd look at its use and we'd look at ongoing maintenance. But through the use of sensors, through the use of, say, the power used, the door opening, the loads in the lift, the sound, temperature, all these are now monitored. So ThyssenKrupp offer a service. So not only do they make the lift, but they guarantee the lifts will be up and running much for greater efficiency than conventional lifts, because they offer this service to those who buy it. So this idea of servitization, you not only make the product, but you supply an innovative service around that product. And this is extremely valuable, because one lift going down in this building is of enormous cost in terms of people's time. Another example of where smart technology is being routinely applied is in shoes, just like this one. So the one on the left is from a company called Lenovo. On a week where we've had Valentine's Day, the idea that your temperament could be exhibited on your shoe. So it displays your mood. But it also tracks and monitors. It also provides maps. So it provides details in terms of the environment, the sense of what's going on, but also measuring information about the person wearing the shoes. Another company using this is Nike, and the information can be downloaded to your device, your mobile phone, with respect to what's going on with respect to the use of the shoe. But not only to that device, it also goes more broadly. So for example, that can be relayed back to the factory. So the information in terms of the use of the shoes. So obviously, if the manufacturer finds that their shoes are being used more regularly, it means that there will be demand for that particular make. Or if the shoe is sitting on not being sold in the shop, it will also see, because there's no movement in the shoe. So it can change its supply chain to address that, not only in terms of its manufacturing activities, but also in terms of who it links with in that supply chain. So that's that idea that your customer, the sensors are informing what your customer is doing, but it's linked all the way back through procurement to what is happening in the manufacturing plant. So we can look at this in terms of the Internet of Things, in terms of manufacturing, and look at the individual stages. So if we look at it in terms of the manufacturing plant, we can address things like predictive maintenance. We can see when a machine is going to go out of specification. We can look, as I said, in terms of raw material supply, or where components are within the plant. We can also address it in terms of the global facility inside. How does one facility compare with the next? Also in conjunction with the customer site, with respect to how the product is being used. In the case before, it was in the case of runners, but here we can look at how that product has been performed or performing, or if there's a, for example, if you like the COVID vaccine, if the temperature has gone above a certain level, that can be monitored and sent back in real time to give a warning, say not to use it. But it also will indicate where we need to go going forward, but with R&D, with management or procurement, all those aspects, all supplied through those IoT sensors. So the supply chain has changed then from a linear supply chain where you look at development, sourcing and delivery and wait until, well, has it been sold or not, through a much more digital supply chain where you get continual feedback, where you can look if product is being sold or not, you can decide on which product lines are being used and get much more efficient use of the equipment through those digital supply chains. One aspect of this, not only do you become informed about what's going on with respect to the manufacturing operation, you can also become that the actual customer can request changes in the product when they're designing it, and those changes can be implemented during the manufacture of the product. So this idea of mass customization within certain limits or individualization of it. So you move from Henry Ford's famous dictate that you can have any color as long as it's black, through to you can have any color you want as long as it's within these 10 ranges. You know, it has come true fruition. Through this Internet of Things, therefore, the ability to obtain sensor data, the ability to upload that to the cloud, to use data analysis in terms of capturing that information and feeding it back gives us an insight. We talk about it as an intelligent system. And that's fine in terms of, say, anomaly detection. For example, you can find anomalies in a process and you can decide what to do with respect to that process. But in many cases, that's one element of what's going on. You need to get a much deeper insight. And for example, modeling of the process or modeling of a product can help in that way, as long as it's informed by what actually is going on. So when we combine these together, we talk about it in terms of what's called a digital twin. It's a cyber version of the real thing. And you can carry out many experiments on that digital version, which would simulate what's happening to the real version. Now, in general terms, rather than a model of the real thing, what you're doing here is informing that digital version with what's happening in real terms by the actual experimental version, or the version within the plant. So it continually provides information back. So the sensors and big data are continually informing the digital version, and you have these process feedback loops. So how has this been applied? Well, one of the first companies to do it, and perhaps not surprising given the cost of turbine engines, has been companies like Rolls-Royce and GE. They have digital twins of their turbines in aircraft. They use them with respect to information about how the engine is performing, when it's due for repair. If you take GE, they have about 13,000 civil aerospace jet engines at any one time in operation. A lot of their operation activities are controlled from the UK. They monitor what's going on, and they sell a service to the aircraft companies like Boeing in terms of the use of their equipment. So they provide real-time information in terms of the jet engine, because if the jet is going to go out of service, they need to know before they have passengers on board. They can actually schedule in and predict what is going to happen. So overall efficiencies are improved enormously through the use of these technologies, and particularly around the prediction part. But it's not only jet engines. More recently, they've also carried out studies or digital twins of the undercarriage. It's every element in terms of the process, the product. You can have a digital twin with respect to that. In addition to the digital twin, we also talk about a digital thread. And I've taken this image from Deloitte of an additive manufacturing process. So right at the center here, you have the process where you're carrying out the printing. You can have part inspection, as shown here. And the information from that is fed back in terms of the CAD. So you have this link between the design, the manufacture, the inspection, and end use, and the continual feedback. So this idea of a digital thread linking all aspects in terms of the process is very important, of which digital twin can be of a specific part, be it the product process within that. Some example of the type of work we're doing in this area is shown here. So this is a production scale metal additive system. What you're seeing is a laser melting the powder, and you can see some circular parts here. When we printed these parts, we could see defects in the parts. This is what's called a CT scan, and an X-ray image showing where you have a defect. But during the process, the data that we were obtaining from the process, we could also identify and predict when the actual defect was going to arise in real time. So seeing the data in real time, you can make a decision: can you address this defect? Is it significant? Or is it something that's so severe that you need to stop it? Now, this is much more than just simply a single layer where you obtain a defect. You can look at multiple layers. You can combine defects such that you can see the overall impact with respect to the process. This here is an example of a catastrophic defect, where what was happening was we were producing this lattice type structure, which is used, for example, in medical devices for bone ingrowth. And we had this triangular defect within the structure produced because a wiper was laying down the powder, and as it laid it down, a small little nick formed, but it actually, over time, it actually came back such that it wasn't there. And what we've been doing is comparing two different approaches to looking at that defect. So here you can see the normal operation, again, normal operation, once it got past the regime where the defect was. And you can see the two approaches to looking and comparing the data generated. So in this case, we identified 31 layers that had defects. We use what's called a student GESD approach. It's a statistical analysis approach. This here is called a stream approach. It's using machine learning to carry out the same process. In this case, we identified 51 layers that were defective. So which approach is giving the most sensitivity with respect to the defects within the structure? Taking this information then, and along with modeling information, process setting, historical data from what has gone before, combining it with machine learning, and we can use this to help us predict a model for defects, which will tell us what is the recommendation of the level of defects with respect to that structure. Is this catastrophic? Is this something that you can alter the process? And can we go back and tell the operator these are the conditions that you need to do to change the process and conditions? So this is an example of a digital twin developed for looking at processing issues as opposed to product performance issues. Now, apologies, this slide has a lot of information on it. I just wanted though to help summarize this area of a smart factory. We've talked about the operations part, the digital twin, the additive manufacturing, but you can also apply the use of Industry 4, for example, augmented reality or AR is one aspect of it. Inventory tracking, I've talked about in the sensors and analytics in terms of it. Quality inspection, you could see from the work we've been doing, that's clearly an ongoing issue. Predictive maintenance, again, augmented reality is extremely useful there because it can help train and identify where defects are. And finally, the area of environmental health and safety, such that warnings, sensor data can say, look, you have a problem, you're approaching too close to equipment, or there's been a leak, and that information can be relayed directly through IoT to devices. So to summarize then, in terms of the value drivers behind Industry 4, I think you can see the time to market, identifying how to make a product more efficiently, how to look at the robustness of that product, how to play around with the designs and see what it looks like in a simulated version can help time to market. We can also look at it in terms of how we look at different product lines and address the supply demand and match that much more effectively. After sales, we're all used to kind of working on our laptops, and if there's a problem, we can phone in and data is supplied directly to the manufacturer with respect to issues there. Looking at quality of address, labor, the downside of labor in terms of Industry 4 is going to be a decline in manufacturing labor, particularly due to automation, and I want to address that now. Things like inventory, the stocks that we have, what is the demand like? Can we relate that to the raw materials? And you have machine-to-machine issues where a machine will tell a separate machine, look, go and order stock because we can see that you need it here. It becomes a lot more automated and far more efficient use of assets. So Industry 4 impact is much higher efficiencies, much more individualization, the more sustainable operations, and overall more profitable as long as it's done efficiently and it's designed to meet the individual needs of the manufacturer. I want to move on now to talk about manufacturing employment. It's very much related to Industry 4 because as I've highlighted, the impact of Industry 4 is going to be a decline in manufacturing jobs. This is an interesting graph from the United States. It looked at manufacturing employment between 1947 and 2011. And you can see this rapid fall off. They lost about 1/3 of their manufacturing employees in the 10 or 11 years from 2000 to 2011. Now, that caused a lot of social issues, and you could see it in terms of blaming China in terms of that, but that's only part of it. In a sense, the employment declined, but actually productivity continued to rise. So that change was largely due to automation, and the automation of manufacturing had a dramatic impact with respect to jobs. Now, what we're looking at here is the period, a third reduction in an advanced economy between 2000 and 2011. But if we actually look at what the impact of automation will be more generally, this is a report by Bain who looked at this area and said, actually, if you look at the period from 2020 onwards, the impact is going to be far greater. This is again in the US, and it's a service sector as opposed to manufacturing sector. And in a certain extent, manufacturing has already lost a lot of its job, and there will be further losses, particularly in manual jobs. But you can see here that the scale of the impact of automation and some of these digital technologies will be quite enormous with respect, particularly over the next decade. And the impact of that with respect to livelihoods is going to be quite considerable, and the ability to reabsorb workers from that sector and the importance of redeployment and reskilling is going to become increasingly important. Well, what's the situation then with manufacturing? If you look at it in terms of manufacturing, far fewer jobs directly in manufacturing, but far more outside that. So it's been estimated that every job in manufacturing will create between 3 and 15 jobs elsewhere in the economy. So there's a multiplier with respect to manufacturing associated with more innovation, components, education, for example, because of the skill levels. So much more highly skilled jobs and many more jobs elsewhere in the economy. And it's because of that there is considerable interest with respect to kind of attracting these high-end manufacturing jobs going forward. Some examples in terms of these new roles are digital skill jobs, which weren't there in the economy previously. There will be growth for those who win that manufacturing employment. There'll be reshoring taking place because the benefits for low-wage economies in terms of low skills, because of the type of manufacturing where it's changing very quickly, those long supply chain issues would become a lot more problematic. And supply chains are also problematic because if they're too regionally located, as we saw during the pandemic. And this change to servitization, this move, as we saw with Rolls-Royce, where you supply the engine, but you also supply a service, and that service can be extremely valuable in terms of the company going forward. So the final part of my presentation is going to talk about, okay, so there are very high value added jobs in manufacturing, but the issue is how to retain and how to grow those. So I just want to briefly talk about what is that impact more generally. And to begin with in terms of this is to just look at the factors influencing manufacturing growth in general. You can see a range of issues. There's resources, availability of power. There's the market forces close to your market in terms of where you're going to sell. There's the training and capability part, and then there's the government. And for example, Ireland has benefited enormously from low corporate tax in terms of companies coming in, but that has been slowly eroded because other people are kind of matching that because they see the value added with respect, particularly to those manufacturing jobs. So what's happened? Well, an example is the Catapult Centres in the UK. They're very significant investment there with respect to it. And very recently, the UK announced a new city deal, Catapult. Belfast will gain from that, for example, with respect to the expansion of these Catapult Centres. These are technology centres closely related to industry. And there's been a number of studies where the return on investment in terms of these centres is quite considerable with respect to jobs created and employment and higher productivity. In China, they have their Made in China 2025 program. They've highlighted 10 areas as shown here. And amongst them is advanced medical products, which is obviously one for which Ireland is competing directly. But you can see some of the other areas that are highlighted here. So China is investing very large amounts in developing and moving up the value added with respect to its manufacturing, because the costs in China in terms of employment are beginning on the East Coast of China to certainly match, if not exceed, Ireland's. And that's an issue for them going forward. They have to increase their value added. So, in fact, looking at the Made in China 2025, the original budget for that was 300 billion. And as a result of COVID-19, they recently announced they're increasing that to 1,400 billion. So an absolutely enormous investment in terms of high-tech industries. Part of that is a reaction to some reshoring associated with that regional kind of issue with respect to supply chains. The UK, in addition to the catapult centres, they've recently announced their Advanced Research Project Agency, ARPA. It's not unlike the defense DARPA in the USA, very much focused though on innovation, close to market activities, and looking at those clear sky research, well, not clear sky, but closer to market aspects. Finally, then in the United States, you can see Biden here, the future will be made in America. That focus on manufacturing locally, and as part of his program for government, he talked about 300 billion investment in breakthrough technologies over 4 years. So this is a very large investment that we're seeing internationally in some of those bigger players, which Ireland can't compete with due to the scale. But in terms of our own sectors, it's interesting, The Economist had an article which talked about the Chinese investment, and where Ireland is located at the high tech, high value added manufacturing is exactly space that China is targeting. And it's just a reflection going forward of the competition into this space because of the wealth that it generates for a country. So how does Ireland compete then? Well, unfortunately, our level of expenditure in terms of R&D is relatively low compared with our competitor countries. Now, if you take the value here between 2014 and 2015, we dropped from about 1.5 to about 1% of our GDP. Now, part of that is because of changes in tax, and our GDP went up enormously. But in terms of GNP, our actual valuation in terms of the economy, we're spending around 1.5% equivalent to other countries, but the average within the EU is 2% of GDP. If you look at countries like the Nordic countries, Germany, it's over 3% of GDP. So we're significantly below the level of expenditure in terms of R&D there where we need to be to compete even at a level playing field. An interesting graph is this one here. It's from the OECD. They carry out a country profile looking at the impact on manufacturing in terms of access, market openness, society, and jobs. And I've just highlighted some examples where Ireland are doing well, particularly ICT patents, digital delivered services, trades, for example. The black dots are the norm. The circles then are where we're actually located. Overall, Ireland is doing well, but it's interesting to see that where we're not doing so well is in the area of ICT investment intensity and startups. And they reflect that low local investment in terms of R&D expenditure. We're also weak with respect to young female coders in particular. That absolutely stands out. But overall, Ireland does well. But if you look at, this is a fourth European company survey, which was carried out by the European Union Foundation. They found that if you looked at digital analytics, that Ireland's, in terms of manufacturing, is at 33%. That of the European average is at 45%. So there's definitely an issue with respect to Ireland, with respect to our competitiveness going forward, not applying some of these technologies. The American Chamber of Commerce recognized this last week to come out with a recommendation of 4 technological areas linking the industrial sensors and IoT, or industrial Internet of Things, is here. That's system integration and big data, which I described earlier on. The AI and robotics has been critical. The idea was to sense what's going on, capture that data, interpret it, and to then act in terms of it. And it's just one example of the need for investment, where we're seeing other countries putting in infrastructure to help link between what companies need and the education system. So finally, in terms of concluding this section, say, look, Industry 4 has enormous potential in terms of efficiencies, reduced downtime and productivity, new activities combining service, traditional manufacturing activities, this servitization role, certainly reduce jobs in manufacturing. However, there will be higher value added jobs, high level of competition for manufacturing employment. Ireland has done very well to date, particularly due to its R&D investment and its combination of local skills combined with foreign direct investment. And some of those foreign direct investment, a number of them are world leaders in terms of Industry 4, but there's also a large chunk of the economy that isn't digitalizing, as I indicated in the last slide. And that's going to affect our competitiveness going forward. So that provides a summary in terms of this element of the overview. I'm going to hand over now to Colin, who's going to talk about some of the work that's ongoing.